All right. I am going to, like I said, lecture a little bit, some things that we need to know in preparation for today's lab. Now, I say we need to know, yeah, you can go through the lab without knowing these things, but it'll help the lab to be more meaningful, I hope. So, one of the things in physics is, as with any discipline, we have our own vocabulary. So, in the calculus-based class this morning, I talked a little bit about some of the words, but words that you use every day, like energy, will mean something different when we talk about it in the physics classroom. And other words that we don't use regularly, like velocity, are very specific. So one of the things we have to learn in this class is the meanings of these words in the context of physics. And so, of course, I will be trying to introduce jargon and explaining what it is and not just expect you to know it, but it is something you have to learn. So the first words are speed and velocity. So how many people are confident that they can differentiate between speed and velocity? All right, then this is a really good one to start on. Speed. What is speed? Good.
Speed is how fast you're going, but not in a direction.
Right. Speed is how fast you're going. It's the distance you cover per time. Velocity has direction with it. So velocity has direction. So I can walk 4 miles an hour, or I can walk 4 miles per hour east. 4 miles per hour east is a velocity. 4 miles per hour is a speed. On the perusal, somebody said something similar. We have the words displacement and I think it was distance. And they said, so the distance is the absolute value of displacement? Fundamentally, yes. In fact, the absolute value symbol is what we use when we're doing the process. So it's taking the size, what we call the magnitude of the value with its units, but not the direction. So speed, a scalar. The name for something that has just magnitude without direction is scalar, S-C-A-L-A-R. Velocity is a vector. Vector is the name for something that has direction. So this is very nice. I get out my purple pen. And that did not write. It's supposed to. This also worked in practice. Oh, I've got to hit this button first. Nope. Okay, you saw. I hit the button for pen. And it dings instead of working. Okay, well, I won't be annotating much today.
Okay, so you're clicking it with the pen.
No, I'm not.
Maybe it's your finger.
Use my finger? No. But who knows? So velocity is a vector. It has direction. Speed is a scalar. It does not. Mass and weight. When you step on a scale and it gives you some unhappy number, if you're like me, it has units. What are the units for that number? Okay, pounds, kilograms. Pounds and kilograms are fundamentally different things. They're not both weights. Only one of those is a weight. How many people knew only one of those was a weight? Okay, we got a number, right?
Oh.
Or were you? Yeah. I thought you raised your hand before I asked the question. That's all right.
No, my bad.
Okay, so pounds are a unit of force. A force is anything that pushes or pulls. And weight is an example of a force. It's how much you're pushing down on the ground because of gravity. So pounds is a correct unit for weight. Where does that leave the kilogram? Kilogram is a unit for mass. It's a measurement of basically how much stuff you have. If you want to get all super technical, there's two masses. There is one mass that is a measurement of the gravitational force. A measurement the gravitational force is proportional to. And then there's the other one that is the inertia. Inertia is measured by mass. But fundamentally, it turns out no experiment has ever been able to differentiate the two, so we just have one named mass. And the unit of mass in our standard system is the kilogram. weight, a force, we had pound. Pound is the imperial unit for force. We're not going to use pounds in this class except for if you have an annoying problem that asks you to convert from pounds to newtons. The newton is the standard unit of force. And we'll get into that later. I'm not going to go into the unit of force right now. So kilogram is a unit of mass. That is the metric unit for mass. Does anyone know what the imperial unit for mass is? It's slugs. So you have a mass of 200 slugs or whatever. What?
Slugs.
Slugs. Like the University of California at Santa Cruz banana slugs.
Or shotgun shell.
The what?
Or shotgun shell.
That's a shell, not a slug.
Well, no.
Okay. Yeah, so slugs are the imperial unit of mass. Nobody ever uses the imperial unit of mass. And so we have this odd dichotomy that people use the metric system, use an incorrect unit when they measure their weight. Instead, they calculate the mass based on their weight. So mass and weight are completely different. And it's an important distinction we have to learn. Right now, it may be confusing. Units are really important. If you just have a number without units, it's useless. If I tell you my home is 0.6 away from here, you're like 0.6 what? 0.6 steps, like that's your home? Or 0.6 furlongs, 0.6 meters, 0.6 miles, that's the correct one. 0.6 kilometers. You need to have units. So when we're doing lab, every value needs to have units. Now, every now and then there's something without units. I won't give you examples. But almost everything has units. And if there are units, you need to say which units you're using. So if you put a value in your lab report that doesn't have a unit, our TA, who is Andrew Cabrera back there, he will mark off 2 points from your lab for not having units. Now, he's not going to do it every time because somebody can run to zero real quick if they have a whole table of data and they didn't put units anywhere. But it's an important thing.
And you just put units at the top of the page.
Yes, when you make a table, if you put your uncertainty and your units at the top, it's implied that everything in that column has it. Okay, so having your units is important. So standard units, the second. The second has been defined since I was less than a year old to be this number of wavelengths of a very specific transition in the cesium atom. Obviously, no one's going to memorize this. Don't worry about it. But we have a very reproducible standard. Any lab in the world can get some cesium-133, and that cesium-133 then will be putting off this wavelength, and they can calibrate a meter based on that. Now, somebody being Sarah, what kind of equipment do we have that can measure this? We actually do have very accurate spectrometers. You can make them with diffraction grating that actually probably can, to within very small uncertainty on that number, measure. So it is a possibility. It is something. So the second has a very standard definition. Now, where's the second come from originally? Well, 24 hours in a day, and each hour is divided up into minutes, so there's 60 minutes in an hour, and 60 seconds in a minute. And so the mean solar day, the average time from noon to noon going throughout the full year is 24 hours. That's the definition that they started with. And then dividing that by 3,600, you get to seconds. And then they use that to match up how many of these wavelengths it would have to be for the distance light travels of that many wavelengths. Yeah. I probably said something wrong. But it's something that can be done. Next, we have the meter. The meter, distances, we use the foot a lot, right? What's the definition originally of a foot? Yeah, it's how long the foot of the king is. So if you have a taller king, the foot is longer. If you have a shorter king, the foot is shorter. And so the foot is varied over time. So you have things like Napoleon. What do we all know about Napoleon's size? Is what? Okay, he said he was like 5'2". Here's the thing. He was 5'2", measured in the French inch of the day. And that 5'2" would translate into something that's somewhere between 5'6" and 5'7" today. And for his time, that was tall.
Really? For him, really.
So compared to the people of his time, he was actually above average.
I will compare this to the French because I know the Dutch are more than
The Dutch are the tallest people on earth, in case you care to know, which Russell certainly does know. What if you don't know Russell? Russell knows more trivial facts than anyone alive. You should be on Trivial Pursuit or, you know. He's constantly teaching me things. It's the truth. Okay, so the foot is just not a very good measurement. My understanding is a yard is the distance from the nose to the fingertips, not even tied to the foot initially. So when scientists want to get something standardized, they tried to calculate 1/10,000,000th of the distance from the North Pole to the equator along the prime meridian. Now, yeah, their surveying wasn't all that great, so they weren't dead on anything. But that was their calculation for what a meter was, and then they engraved 2 marks on a platinum iridium bar. And that bar was stored, and anytime somebody wanted to check a meter, they'd have to bring my meter stick compared to those 2 marks and see if it's right. That's not very useful, because you have to go to see that bar to measure its length. And so now the meter has been redefined as this is light travels in 2,709,458 of a second. Yep, that's it. But it's something that's completely definable. This was defined when I was in college, probably my junior, senior, or not college, but high school, my junior, senior in high school. And so now the meter is very standardized. Then we have the kilogram. Up until 2019, that's this year, the kilogram was the mass of this ingot of platinum iridium that was stored in a double vacuum chamber. There's a bell jar, inside that is another bell jar. Each one is independently pulled down to try to get the best vacuum they can. But how are you going to compare to that? That's pretty much a useless standard, isn't it? And so this year, this summer, or well, this spring, they changed the definition. So the kilogram is defined by taking the fixed number of the Planck constant. So the Planck constant actually changed this summer. So the Planck constant, like the speed of light, is now considered an exact value. And like if you try to measure the speed, what you'd really be doing is redefining how long a meter is. If you tried to measure the Planck constant, you got a different number, you'd be redefining some other constants. So this is something that's all new to me. Is it something you're going to be tested on? No, you're not going to be tested on these definitions. But I want you to know that scientists have actually worked really hard to try to make the unit something that's verifiable. Yeah. You look perplexed.
How does joule seconds transform into kilograms?
Okay, so a joule is, most of you, I assume, don't know what a joule is. I got to figure out what in the world happens so I can't write on here.
It's something of work. Yeah, it's a unit of work.
Yeah, I think
A joule is a unit of work. A joule is a kilogram times a meter squared divided by seconds squared. And so it has kilograms, meters, and seconds in it. So if you use the definitions of meters and seconds, you can back out to kilograms. Okay. We use the metric system. We call it the SI system. And you're like, SI, what does that mean? And I don't speak French, but it's like Système International or something like that. The United International System. So this SI system, we have those base units I've just talked about, and then we have prefixes that we use with numbers to make life easier. So here's the base units. I'm sorry, I got my spacing off. I was trying to put stuff together. Length is measured in meters. Mass is measured in kilograms, time in seconds. Electric current, we'll get to that next semester. We're not going to get to that this semester, is amperes. Temperature in kelvins, that we will cover this year. The amount of the substance is in moles. You probably already know that, or else you have a question.
Is amperes the same thing as amps?
Amp is just an abbreviation for ampere. Or if you want to be accurate, since it's a French dude's name with a couple accent grave and accent aigu, it's ampere. But like I said, I don't speak French, so I'm just, winging those. And then finally, luminous intensity candelas. We will never use the candela in this class. But those are the base units. Everything else is derived from those. Yes?
Should we know these or always?
You don't have to have them memorized. You will be using them enough that you will know them. One thing that's kind of funny is I actually should check again. I think the coulomb is now the base unit instead of the ampere. I didn't check that before today's lecture. Part of the change in units that they did this spring, or this past spring. Russell.
Why is the kilogram the base unit, not the gram?
Very good question. Why is the kilogram, kilos a prefix that means 1,000? Why is that the base unit? Honestly, I don't know why. It's the only one that has a prefix though. Oksana.
The electric current is I.
The symbol we use for electric current is I. The unit for electric current is amp. It gets more interesting when we get to voltage. The symbol we use for voltage is V. The unit we use for voltage is V. The name for voltage is actually electric potential. But we call it voltage because we use the symbol volt, or because the unit is volt. And so it's like calling current amperage, which some people do that as well. Other questions? Okay, now derived units is when you take something that's a combination of units. So for instance, I wish things were working. You believe me, I practiced this beforehand and everything was working before class. Hey, look, it moved them. Maybe that will, no, of course not. Why should anything work today? Hey, okay. Apparently I had to select with my finger. So this is a derived unit for force. We define this as 1 Newton. 1 Newton is 1 kilogram times meter per second squared. If you try to make sense of that, it doesn't by itself. Like you think of what is a kilogram meter per second squared, you don't come up with anything physical. I mean, something as simple as, what is the second squared? I mean, you can't square time, but it has a use in our calculation of units. And so we'll learn about those coming up. Models, theories, laws, principles. Somebody was asking, what's the difference in a principle and a law? And the textbook says, well, a principle is more limited, a law is more general. So a law always applies, and the principle only applies in this special case. It's kind of a thin separation. So while they're not the same thing, they're pretty similar. And so you have like, it's more than semantics, but it's something that I don't care about, honestly. I mean, why should we sit and quibble about if this is a principle or a law? Another person, I remember Sarah's comments, was like, why do we call them laws if they're not immutable? Right? Our laws of physics are never proven correct. The whole scientific method that we talked about in class yesterday. You observe something interesting. You guys all got your observation for today's lab figured out? Yeah. All right, Max, yeah. Then you have your hypothesis that is going to explain why that observation thing occurs, is based on scientific ideas and makes testable predictions. And then you test predictions, and if it confirms your prediction, then you go back and you test differently. If it disproves your prediction, Then you know you're wrong and you go back and you revise the hypothesis. And so this process doesn't have an endpoint. In theory, it has an endpoint if you do an infinite number of experiments testing every single possible prediction in every single possible way. So by definition, we can't prove anything to be true for our scientific laws. We can disprove them easily. You know, if I say, when I take this and I drop it, it's going to fall at constant speed. That's what Aristotle believed. So everybody believed for like 2,000 years. One experiment can quickly disprove that. But if I say, when I drop it, it's going to fall with a constant acceleration of 9.8 meters per second squared, one experiment can confirm it, a million can confirm it, but it's still not proven. So answering a couple of the questions that people talked about in the reading, the planetary model is an example of a model. A model is not factual. Here is another model. This is called the celestial sphere. The model is that all of the planets, stars, are on a fixed sphere that's rotating around the Earth. This is, again, Aristotelian thought. Aristotle believed this to be true. Now we know it to be very untrue. And yet we use it. We use it because it's a useful framework for helping us to see how the system works, even if that's not really what's going on. So a model is a framework to help us in thinking about something. I shouldn't set this down since this is my clicker to advance. A theory is something that started as hypothesis. Hypothesis, educated guess, right? It's based on scientific knowledge, so it's educated. But it's still a guess. You don't know what's right or wrong. In your hypotheses for the lab, you're not going to be graded on were you right or were you wrong. You're going to be graded on going through the process and being legitimate. I mean, if you come up with something that's just inane, you might lose some points. But in general, it's if you've done the process right. After you studied it a lot of times, you start to gain confidence. And so, dropping a ball a number of times and doing a bunch of experiments on the dropping ball makes it so that we're very convinced about some things like the law of universal gravitation. And so it moves from being a hypothesis to a theory, and then as it becomes more accepted, if it's broad like universal gravitation, then it is called a law. So laws are broad and are very heavily tested and believed to be true. Theories are a step below that in terms of how broad they are and how much they've been tested. Because we're a Christian institution, and I personally believe in a literal 6-day creation. Whether you do or not, that's your business. A lot of times we have debates that come up, especially in our church, between people who believe in evolution, people who believe in creation, people who believe in young earth creation. There's lots of variations. And something that creationists will say is, well, evolution is only a theory. How many people have heard that? Evolution is only a theory is a statement of ignorance. That's a statement from somebody who doesn't know what a theory is. Right? Theory doesn't mean, it's just an idea. It means it's an idea that's been tested thoroughly. Now, I told you I don't believe the theory of evolution is correct. But, in fact, we can go on a lot of philosophical talking about that. But just because it's called a theory does not mean, the scientists don't believe this, or it's just a guess they threw up there. No more than the theory of Newton's laws or anything else we learn in this class is false because it's a theory. Obviously, what we're learning in this class is the best knowledge we have about science. Well, I say obviously. We will learn things that what I teach you at the very beginning is an approximation as long as you're going much less than the speed of light. which generally makes sense because none of us are going to travel anywhere close to the speed of light. And so later on, we'll clarify those little things where we kind of glossed over. Speaking of glossing over, you should know in physics we make a lot of assumptions that we know are incorrect, but that make it a lot easier for you, the student, to work with. So for instance, for lab today, we're going to be dropping a ball. Well, as you drop that ball is going through air. It has to move the molecules of air out of the way. And so that provides a resistance force. We ignore that. Because it's small, we say its effects are so small, we're not going to observe the difference between if there's air resistance or not, and we ignore it. Now, if you were to hold your hand out of your car, you're driving down the road, you can definitely feel it. You can't ignore it. The reason we don't get absurdly high fuel economy when we're driving on the freeway is because air resistance is very significant on our cars. It's taking a lot of energy to keep the car moving because of the air. Question?
So those questions on that little test we took, where you're supposed to ignore air resistance and things like that, what it did say?
Yes, if it doesn't say to use air resistance, ignore it. And you can make arguments for a lot of things, but you want to ignore things that are going to be of immaterial amount, unless you're told to use it. Okay, moving on. The law, okay. Newton's second law. You might have noticed it's my comment. Actually, they're all my comments. The ones for me, my son, and my wife, but you can't tell. Our textbook has F equals MA without the summation sign. That's a pet peeve of mine. It's not correct without the summation sign. It's just not. And so, just know that's something you can lose points on just, if you aren't paying attention. So how do scientists explain things? Well, we need our explanations to be based on first previous knowledge. Remember I said based on scientific ideas. So you read other people's ideas. Then after you've read those ideas, you're going to test to see if, what you're observing matches those ideas. Invent an explanation. Of course, we're talking devise experiments to test it. Report the results. This is the textbook's list. You'll find different lists depending on who writes it. Reporting the results of experiments. You don't do that after the first experiment. You do that after you've done enough experiments that you're thoroughly convinced. And then you report those results. Back when I was in graduate school, you wrote an article, you submitted it to a referee journal, and then your article is sent out to referees, other people who are experts in the field, and they judge it. They will send back and say, this is wrong, or this should be clarified. After it goes through that refereeing process, then it gets published, and then everybody who finds it interesting tries to prove you wrong. And hopefully they don't. But that's the way it works. These days, with the internet, you put preprint on archive and start testing it there, and it's a little different. Peer review is not what it used to be, apparently. But that's an important part, and you're going to have criticisms because some people will have a vested interest, like, you're saying my idea is wrong. My start in science, my first conference I went to for my master's degree, my professor said, there is this thing that people are calling anomalous shock cooling. Anomaly means it's not normal. Shock waves traveling through a liquid were causing, they thought, cooling in the liquid. And if you think about it, a shock wave is putting energy in. And when you put energy in, since I told you yesterday, temperature is a measurement of the average kinetic energy, so it's proportional to the energy there. Put energy in, the temperature should rise. And they were seeing drops. It is possible in some weird situations to put energy in and the temperature to drop because you're changing phase. My professor's like, I don't believe, they're finding a lot of liquids with this anomalous shock cooling. I don't believe they're measuring what they think they're measuring. And so he said they're using sapphire as a window material, and he set me to measure the optical properties of sapphire when the shock wave goes through it. And I measured and found that the sapphire was becoming opaque when the shock wave went through. If it becomes opaque, the measurement they're using to measure temperature is called pyrometry, where you're looking at the light, if you will, the electromagnetic radiation coming from the liquid to determine its temperature. And so if the window that's between the liquid and you is becoming opaque, that's going to change your measurement. And so I went to this conference and I gave my talk. Good talk. For sure. It's been a long time. About my research and how it wasn't actually cooling, it was a change in the sapphire material. And then I wasn't at this talk, but another talk later in the day, one of my colleagues was at, and it was on the knowledge shock cooling. The guy gave his whole talk. And somebody says, I was at a talk this morning. It said that it's not shock cooling at all, it's the sapphire. I entered an entire field of shock dynamics research right there. So I was definitely on that criticism part. I'm really proud of it, you know. I ended a field. It was awesome. But that's part of science. Now we have a preponderance of women in this class. I have read articles actually by women trying to explain why physics doesn't have as many women as it has men. And one of them was because women aren't comfortable with this criticism nature that is implicit. It's just part of what we have in science. And so that was an argument for why women aren't as represented as men. I don't really buy it myself because you won't find anyone less argumentative than me. I don't want to argue. I said that all wrong. You know what I mean? I am not a confrontational person, so I made it through. I don't see why, if there's a difference between men and women in confrontation, it should matter. Okay, the scientific method, we've already talked about this. For your lab, remember you need to observe something interesting, which is going to be about something dropping. Develop a hypothesis that explains the observation, is based on scientific ideas, and makes testable predictions. And then you need to devise a test of the prediction. Your test today is going to be comparing the time for a ball to drop 1 meter for the time for it to drop 2 meters. And your test is specifically going to be, does it take twice as long to drop 2 meters, more than twice as long, or less than twice as long? Those are the 3 different possible outcomes you're going to be comparing. And then this is what you do. If it passed the test in the scientific method, then you go back and you test differently. If it failed, you go back and modify the hypothesis. Okay, mathematics. I have this in here just because I myself get confused. If something increases by a factor of 2, I'm fine with that. You multiply it by 2. But if it decreases by a factor of 2, I get a little confused, but that means you divide it by 2. Percent. I don't know about you guys, but I've known people that believe if they have a 50% off coupon and they go to the store and they have a 50% off sale, that those items are now free. Okay, you're laughing. When I was teaching at PUC, our financial vice president said that because our pay went from 148% of a number to 150% of a number, we all received a 2% pay increase. Not so. Some people don't do good at math. Okay, I shouldn't say that. So percentage means per 100. And you probably all have a good feel on that. So if you have a 50% off of a 50% off, how much total is taken off? 25, because it's half of half. Okay. Accuracy versus precision. Sarah gets, you're probably sad that I know who Sarah gets really bent out of shape when people get precision and accuracy confused. So I have to be extra careful because even though I know the differences quite well, I can still make mistakes.
Is that why they have precision
Is that what?
Is that why they have precision rifles instead of accurate rifles?
I don't know. So precision means reproducible. High precision means you can hit it over and over and over again, same spot. Accurate means that it's close to the target. And so you can be very precise with your rifle, but always missing by 2 yards. You're not a very good sniper. You can be accurate and imprecise if you take the average of your shots, they come dead on the heart. But most of them are a meter off in some direction. That's still not cutting it, right? So the goal would be to be both accurate, close to the goal, and precise, reproducible. In our lab measurements, in this lab, it has the explanation for how you really account for precision. You have, okay, how much could I be off? And you have to estimate, for a measurement, like let's say that you are measuring the diameter of this. And so I said, okay, I'm going to use a meter stick. I take that meter stick, and I have to say, now, what kind of errors could I have? One error I could have is if I use the end of the meter stick. The end of the meter stick is not calibrated. I know you can stick it there and make a measurement, but it's not necessarily correct. So that would be a mechanical problem I have. I should just not do that. So I use like 10 to start. And then I have, okay, I can read this, and I can read to a certain number of digits. And I had to estimate a little. How much error did I have in that estimation? One of the important things with measurements is, the meter stick has marks of centimeters, that's what these numbers are, and then it has smaller marks that are millimeters. The prefixes, which you do need to know the prefixes from from femto up to, let's say peta. You should know those prefixes. Centi means 100. That's why it's per cent, per 100. Milli means 1,000. So a millimeter is a thousandth of a meter, centimeter is 100. So these little marks are millimeters. If you can clearly see the edge of something, you should be able to estimate how far it is between the millimeter marks. And so you estimate one digit beyond what it reads. So since this reads down to millimeters, my measurement should read down to tenths of a millimeter. But then I have to estimate how wrong was I? How far off could I have been? And if it's just the scale that I have to deal with, if I don't have to worry about, did I actually have the diameter, or was I a little off? Then I usually say, well, I'm definitely good to within plus or minus a quarter of the separation, which I round to one decimal place, and I put 3 in that digit that I estimated. With this, I would probably go a little bit bigger than that because I have to make sure that I was measuring the actual diameter, not off by a little, because if I go off a little, it's going to be smaller than, what I measure will be smaller than the actual diameter. So when you're doing measurements, you want to think about what could be causing errors in this measurement and how big is each one going to be. The biggest one is what you'll use for your uncertainty. Okay, so significant digits specifically. We use significant digits to track how precise our numbers are, how many decimal places we should have in them. So digits are significant if, number one, if it's a digit that's not a 0, it's always significant. Number 2, if it's a 0 between 2 significant digits. So for instance, 1.01, that 0 is between 2 significant digits. That makes it also significant. 3, if it is a trailing 0 after a decimal point. So let's make sure we're clear on what a trailing 0 after a decimal point is. If I have 1.230, this 0 is trailing because it's at the end of the number. And it's after a decimal point because here's the decimal point in front of it. So that 0 is significant. That 0 is meaningful. 1.23 means I have no idea what digit comes after the 3. 1.230 means I know what digit comes after the 0, and my uncertainty, is smaller. So there's a difference having the 0 and not having the 0. So this is significant. What about that 0? Is that significant? No, because it's leading my number. What about the second 0 there? Is that significant? It's not. It's a placeholder. If you took that number out, the number would change. If you took that 0 out, the number would change. So it's just a placeholder. It's not significant. Now, if you use scientific notation, life becomes easy. In scientific notation, you have It's just a math problem. In fact, in your homework, this is how you have to put it. The homework site does not have scientific notation. You have to put times 10 raised to the 3. It's a multiplication problem. All numbers in scientific notation are significant. That makes life easy with scientific notation. Oh, look, cardinal numbers. I know. Cardinal numbers are like how many steps are in the stairway. There's not 1.3 steps in the stairway. It's always an integer. So those are cardinal numbers, and those have infinite significant digits. So every now and then you'll run into cardinal numbers, and you just have to go and they have significant digits. So now the rules for multiplication with significant digits. If you multiply two numbers, the way you determine is the significant digits is keeping track of your percent error. And so you look at the number of significant digits. The first one, how many significant digits are 1.234? 4. How many significant digits are in 0.123? 3. So you look at those and you say, okay, 0.123 is only good to 1 part in 3 orders of magnitude. 1.234 is good to 1 part in 4 orders of magnitude. So the one with less precision is the 1 part in 3 orders of magnitude. And so your answer is going to be good to 1 part in 3 orders of magnitude, staying with the smaller of your 2 precisions. So the smaller the number of significant digits is the number of significant digits you answer. So that has 3 significant digits. This 2 is a cardinal number, I'm telling you, because you wouldn't know if you just saw it printed, right? So if this is a cardinal number, how many significant digits does it have? Infinite. How many significant digits does this have?
3.
So how many significant digits do you have? The answer? 3. This is how you calculate how many hours or how long a sidereal day is. That's how long it takes for the Earth to do 1 rotation. Most people think it takes 24 hours. After all, I said the average time from noon to noon is 24 hours. But we do a little bit more than 1 rotation in a day. And so this is how you do the calculation. It's 24, a cardinal number, times 365.2422. That's how many days there are in a year. Divided by 1 more than 365.2422. So how many significant digits here? How many here?
7.
7 here?
7.
Here? So when I do this whole calculation, how many significant digits do I have in my answer?
7.
7. 7 because it's infinite, 7, 7, 7. Because 7 is smaller than infinite. Now addition, subtraction, yes.
How do we know that's a cardinal number?
Basically, you have to have something to tell you that. That's why I said I'm telling you. Okay, addition, subtraction is a completely different rule. If I have 98.7 plus 5.67, how many significant digits in the first one? How many in the second one? How many in the answer?
Wait, it would be the
10th place, so it's 4. Your answer has 5 digits in it, but it's only good to 4. So the rule here is a different rule. What you do is you determine what the least significant digit of each number is. So the least significant digit is the farthest one to the right. So here it's in the 10th place. Here it's in the 100th place. The greater of those is the least significant digit in your answer. So if you do this problem, I stack the numbers to make my life easy. That's what you get for your calculation. 103?
Oh, yeah.
Don't scare me, man. So then I just draw a line here at the end of my greater of the least significant digits. And this is the number of significant digits I have. And of course, then you round, so 104.4 would be the answer to correct significant digits. At this point, I have to tell you, your homework site does not honor significant digits. Your homework site simply calculates plus or minus like 2% on the answer, and if you're within 2%, it marks as correct. which sometimes gives you a lot of grace for errors. People make significant errors and it comes out right. Somebody else does the exact same calculation, comes out wrong, and then they come to me, we did the same thing. Well, it marked them right when they weren't right. It marked you wrong correctly. So in the homework, in all your calculations, you should keep all of the digits until the end. Don't apply your significant digit rules until the calculation's over. Because if you apply them early, you threw away some information, making your answer even less precise. But when you get to the end, in real physics, you then apply your significant digits. In your homework, make sure you always keep 4 digits in your answer. If you keep 4 digits in your answer and you did it right, you'll never be marked wrong. If you don't keep 4 digits, even if you did it right, every now and then it'll mark you wrong.
So does that mean like add a couple zeros if you need to?
No, because it doesn't care about the zeros. It's not changing the number. Okay, let's go to look at what we're doing in the lab specifically today. Now I have the whole stinking introduction to the lab guide here, and I'm going to go through just a few of the important things. One is the mechanics of your lab report. Now your lab report is just written on paper, your choice. Then when you're done, you photocopy it. I have some instructions in here on how to use a photocopier on campus to make a PDF document. A lot of people use their phone and use a scan PDF app or something like that. Try to make sure that it's readable though. Some people turn in non-readable stuff. And then you combine them into one document and turn in one PDF document on Moodle. And I expect this first week I'm going to have some people coming and asking me for help. Make sure you get it right. So there's no special lab notebook you need. You're just going to turn in a PDF document. Now your lab report should always start with a title. And the title should be the title of the experiment. So each lab has a title, and today's, I believe, is measurements. So it should say measurements in the top. In the top right corner, put your name, the name of all of the partners you may be working with, and the date on which you did it. Make sure you make your name clear. Don't just have your name as the first among the others. Say, name partners and the other people's names or something like that. So it's clear, hey, this is this person's. Then the purpose. Each lab has a purpose. The purpose for this week's lab, I didn't bring my, actually, I guess I didn't scoot forward, but I'm just going to steal somebody's lab guide because, friends steal. The purpose is to learn how to read some simple instruments and how to handle uncertainties and measurements. That's what I hope you will get out of this lab. You don't have to quote it verbatim, but you might as well. It's not like it's a lot of words. So after that, then you have your scientific method. If before you do your experiment, you consult with Andrew or me, and we actually physically sign on there saying this is an appropriate observation, hypothesis, and test, then you can be sure that except for in your work on it, you won't lose any points. There's 20 points for this scientific method part. And if you check with us before you do it and we sign off on it, you're guaranteed to get those 20 points. If we don't sign off on it, of course, if you bring it to us and we say, no, that's not going to cut it, well, then it won't cut it. So make sure you have these things clearly marked. We want to see observation, blah, so we can identify, there it is. Equations. Every equation you use needs to be listed along with the variable definitions. So in this lab, there's one equation. The one equation is volume is equal to pi over 6 diameter cubed. And then you say V equals volume, D equals diameter. Right, so you need to have that written for the equations. And then somewhere in the lab, you need to show an example of actually putting numbers into that equation.
Random numbers?
No, actual measured numbers. Yeah. Then the procedure. The procedure is probably an annoying thing, not as annoying as, I'm sure, the scientific method part. But the procedure, I don't want you to copy the procedure from the lab guide. The procedure, written by me, is overly verbose. I want to make sure that I've covered every question that I can think of that you might ask. Your procedure needs to be enough that somebody who knows physics, knows the equipment, can read what you wrote and can reproduce the experiment. Doesn't need to have all the nitty-gritty details, but it needs to have enough information that somebody could reproduce the lab based on what you wrote in the procedure. I accidentally skipped over apparatus. The apparatus should list the things that you're going to use and show a diagram of how they're used. Now, in today's experiment, you know what you'd have for a diagram? You'd have a picture of a meter stick with a ball here and something to indicate the ball goes down to the ground. That's all you'd have for the diagram for today. In other experiments, it's going to get a little more complex. Data calculations and discussion is one section that should be a chronology of what you did in lab. And it shouldn't just be data and calculations and data calculations. It should also have the discussion like, okay, now I'm doing this. This happened that wasn't good. You know, I had to change and do this. Those kinds of comments should be there because that's part of the actual experiment. If you're doing a real experiment, if you go to publish it, you need to have that kind of information to refer back to. You know, I did this, had this problem, made this modification, did it again, everything works great, well, except for this, I had to make this change. Those kinds of things need to be in a real scientist research log so that when they go to publish, they have that to back them up. People can challenge them and say, look, right here. And so everything should also be in chronological order. You shouldn't go down here and then come back up here and insert, because that is taking away from the integrity of your report. In the data section, your data should be put in tables if you do any measurement more than once. Almost every measurement is done more than once. For instance, you're going to be dropping the ball 5 times. Then your partner's going to drop it 5 times. You should have that all in a table, which makes it easy to just glance at, and you can see, yes, there's the numbers. I can see a pattern or, whatever. Any calculations are done there in that section as well. Any questions that you need to answer are there. The results has nothing new in it. The results section is a section where you restate only the important outcomes. So like you measured the average time to drop a ball, or the time to drop the ball 5 times. Your important result is the average time you got from that, not each individual measurement. Right, so your important results, the average time to drop 5 times, and your standard deviation for that, and the average time for your partner, standard deviation, the average time to drop 2 meters, and the standard deviation. Right, those are your important results for the first section of the lab. Then we have the diameter measurements where you have similar. So those are just summary of important data. No new stuff is in the results. Also, you have a statement of if your hypothesis was confirmed or disproven. Now, in the conclusions is where you show what you learned. So in the conclusions, you should specifically state why your hypothesis was confirmed or disproven. You should clearly state what you learned in this lab. Did you learn what you were supposed to learn? Was it something completely different? Like, I learned that I could deal with more frustration than I did. Hopefully that's never going to be the case, but it should be the things that you learned in the conclusions. And so here I have a sample lab report, which I did quickly and I made lots of mistakes. So here's my title. Here's me, my partner. I put my wife here as my partner. Clearly stated, nobody's going to be confused which one's me, which one's my partner. The date on which we did it. The purpose, my scientific method, complete with scratch outs. When you're taking data, if you take a measurement and you're like, oh, that thing's wrong, you should still write it down because you took that measurement. But then put a single line through the measurement to indicate that you don't believe this is correct. And you might put a notation on why you don't think it's correct. Part of the reason to do that is the integrity of the data. Part of it is you might later find out, hey, that wasn't a mistake. That was actually what it was. So you never erase. Pencils, when I was in college, pencils were just forbidden. Couldn't use a pencil because you might be tempted to erase. And I've got my test here. And of course, you guys all have this in your lab guide. Equations, I don't know what lab I was doing. Clearly not this one because I have kinetic energy, potential energy for spring. You know, I have all the equations and the definitions of all the variables I used. Here's my picture of my apparatus. Do I have apparatus written somewhere? I probably skipped it. Oh, there it is. Here's my actual apparatus. The procedure, description of what I'm doing in the lab, and then my data. Notice I didn't give myself enough room, and I realized that after I started making my table. So here's my real table. Following through with what Russell said, I have in my table heading the unit here for kilogram. These masses were not measured. They're stamped and assumed to be correct. So that's why they don't have uncertainties, because they're assumed to be correct. Doesn't mean they're correct, mind you. They were at some point. My position, I have their uncertainty. And notice that all of my measurements have the same decimal place as my uncertainty. This one here has a 0 there. That 0 is meaningful. It means I know that that digit's 0. Now in this lab, you still will need to have this number of digits, right? But your uncertainty may actually be a smaller number than or a bigger number than the last digit, because we're doing things a little bit odd, this one. This here, the stretch, is a calculation. The stretch is the difference between this number and this one. And so I'm not requiring you to put uncertainties for calculated values. So the stretch, the force, the spring constant, all of these were calculated. And because they were calculated, you don't have to have an uncertainty there. We're just using significant digits to keep track of it. Here I have a sample calculation showing a couple of my equations there that were used in the table above. Graphs. When you make a graph, I'm not sure if we're doing graphs today, but I'm still covering it. You should have each axis clearly labeled with the units. You should have a title that is actually meaningful. If you put force versus, or stretch versus force, that tells you nothing. You could read the axis and know that. It needs to tell, the title should tell you why you made this graph, why somebody who's reading this graph should find it useful. And just force versus stretch doesn't tell me how it's going to be useful. But if I say it's finding the spring constant, I'm all, oh yeah, this graph I'm going to find the spring constant from. There's the purpose. The data points here, I put dots on the data points. This graph, the data, I actually did take data. The data turned out really, really good, so it looks like my line is just going through all the data points. That's usually not the case. The line should be a best fit line. It's the straight line that's the closest fit you can make to all of the data points. It doesn't necessarily touch any data point. Some people try to first, you need to draw the best line that comes closest to all of them. And then I calculated the slope rise over run. And then there were questions, and so here's my answer to the first question. I labeled it Q-C means question or comment. So Q-C1 is listed in the textbook. Your answer should not require somebody to look in the lab guide. So, for instance, in yours, for today's experiment, QC1 asks you, it asks you to estimate how long it will take the ball to fall 1 meter. You shouldn't just say X seconds. Right? X seconds, nobody knows what that means. You have to have context. So you say, I estimate that it's going to take the ball this long to fall 1 meter. You write that whole thing out. So nobody has to look in the lab guide to figure out what you're answering. And go through the rest of it. A second data table, more calculations, more questions. My hypothesis test, because in this one I have a separate hypothesis test. It wasn't part of the regular lab. My results, notice my results are just short summaries. And then my conclusions, what I learned. And here's some other graphs the computer made for me. Oksana.
Okay, so I thought a hypothesis would just be like one sentence.
There's no rule like that.
There's no wrong. Okay.
Okay, here's some instructions on using the copy machines on campus to scan your documents. In grading your lab report, this is how the grading is going to go. This is all in your lab guide, remember. The header, where you put the title and your name, and your partner's name and the date, that's worth 2 points. The purpose worth 3 points. The scientific method section worth 20 points. How do you make sure you're going to get all 20 of those points? Yeah, you get it signed off before you do the experiment, not after you do the experiment, before. After you do the experiment, well, it's going to go to the grading. Then you have 5 points for the equations, which includes showing the sample and showing the definitions of the variables. 5 points for your apparatus with the picture. 20 points for a procedure that covers all of that you're going to be doing. And 20 points for your data calculations and discussion section, 10 for the results, 15 for conclusions. Yes?
How do you get your approval?
You bring it up and you have me or Andrew read it, and we evaluate, and basically we're grading at that point, but we either say it's okay or no, you need to do this. Okay, because I've taken a lot longer, we only have an hour and 10 minutes left in the lab period, I'm actually going to cut out all of the measurement stuff and not talk about how to use the vernier calipers. The next thing is how to use a vernier caliper. It is something important to learn, but we don't have time to do that today. So let's jump to what we're going to do in the lab. Okay, so here we go. Note, whenever possible, you should repeat each measurement for a total of at least 3 trials, and you're specifically told to do 5 trials for the stuff we're going to be doing. We are only going to do Roman numeral 1. So it's going to stop right there. So if you have not written your procedure, you can stop after Roman numeral 1 because we're not going to do the rest just because of time. Okay, so the next thing, the time measurements. For the time measurements, note you are, for question comment number 1, to estimate the time it's going to take to drop 1 meter without dropping anything. So you're not going to take a ball, by the way, Andy, can you get the ball bearings? You're not going to take the ball and drop it a few times and say, I think it was this much. You're going to just say, well, from my experience, it's this much. And you're going to write down, from my experience, I think it's going to take this long because, I saw David falling off of the desk, and it seemed like it took him that long to fall. Yeah, I know. What were you thinking? After you have made your prediction, then you're just going to drop the ball a few times, and then you have a chance to say, that makes sense, or was I maybe a little bit too long or a little too short? Now, you're not expected to get the right answer. But you can lose points if you have something ridiculous. Like, it's going to take 2 hours for the ball to drop a meter. Yeah, you're losing points. Right? It needs to be something that's reasonable. After you've dropped the ball a few times and you revise your estimate, make sure you give a reason why you revised it, or if you didn't revise it, why you didn't think it needs to be revised. And then it further tells you, estimate how far you could be off, how much error you could have. So you're thinking about what could cause errors. There's things like my reaction time, and there's all kinds of things to think about. And you want to think about what's going to cause error, what's going to be the biggest one, and then estimate your error and why you got that. After you estimate your error and why you got that, then it's time to make some measurements. So you're going to make, I'm not sure where I have it, here it is, under 3. Using your timer, have your lab partner drop the ball from a height of 1 meter, and you measure the time. Not find them? Yeah. I wonder if they're up here. I'll feel stupid if they're up here. Nope, not here. Nathan. That's what I get for telling you. I don't care. Just find places for things. I'll find them after we're done. Your measuring is when you're doing the timing. So you do the timing. If you have a stopwatch like on your watch or on your phone that does to thousandths of a second, you can use it. If not, then please use mine because it apparently has more significant digits. So the timer that I have for you, assuming I can get there, which I think is true, it's, uh-oh. I don't think it is on this. Well, yeah, I can find it a different place. Come on. It should be in this folder. That worked well. Okay, there we go. So it's an app called Timer. So if you run that app, which I may or may not have, see this little timer that came up down there at the bottom? That's the timer that we have for you. You just go to the folder that says Physics 151, start the timer. And the way this works is when you hit the space bar, it starts timing. Now I know it's only showing quarters of a second, but it's actually measuring much more. When you hit the space bar again, it stops it. And when you stop it, you record that number. When you hit the space bar again, it does two things. It resets to 0 and starts. So you don't have a separate reset. You just hit space bar again and start over at 0. So just space to start, space to stop, space to reset and start again. So you're going to measure 5 times how long it takes to drop a meter. Then your partner measures 5 times how long it takes to drop a meter. You record both your data and your partner's data. If you have a group of 3, which I think there'll be one group of 3, or we could have one group of 1. I don't care. It's probably easier to have one group of 1 than it is to have a group of 3 for today's lab. But you want to have everybody in your group's data in your table. And then you're going to calculate the standard deviation average. And you don't need to go work hard to do that. There is a spreadsheet in that same folder that when it comes up in the first worksheet, it just has a place for you to put in the numbers and it calculates the standard deviation and the average. The first one that says statistics. So I just put in my numbers. And my average for those numbers, and just keep the same number of decimal places as you start, or the same least significant digit. So since all mine I had set out to hundredths, yours will be out to thousandths. Just keep out to thousands, so I'd have 2.25 with my number for the average and 0.97 for the standard deviation. And that's where we're cutting it off. You go to the 2 meter dropping so you can do your test, and you'll be done.